Hey everyone, and welcome to today's Explainer. So, today we're doing something a little different. You are officially stepping into the role of an engineering detective. Whether you're studying up for your grade 8 technology exams, or honestly, just kind of curious about how the amazing built world around us actually works, you are completely in the right place. We're going to crack the code on everything from why massive bridges don't just fall down, to how the gears on your bike actually make you go faster. I'll be guiding you through the exact tools, forces, and rules that real engineers use every single day. And by the end of this, you'll be able to look at a real-world problem, evaluate the design, figure out exactly how to fix it, and make sure we're keeping the environment safe while we do it. Sound good? Let's get right into it. Okay, let's open up our training manual for the day. We've broken down these big concepts into 6 super easy chapters: forces and strong shapes, why do structures fail, mechanisms that make things move, reading engineering drawings, taking nets from 2D to 3D, and finally, choosing the right materials. Chapter 1, Forces and Strong Shapes. This is all about those invisible pushes and pulls holding literally everything together. So, what is a force? At its absolute simplest, honestly, simple enough that a 5-year-old playing on a playground could totally get it, a force is just a push or a pull on an object. Think about pushing your friend on a swing, or pulling a little red wagon behind you, right? That is a force. Every single building, bridge, or even your own house is made up of parts called structural members. And these parts have to constantly handle all these different pushes and pulls all day long just so the building doesn't fall down. And here is a perfect example of our very first type of force: tension. Tension is basically just a pulling force that stretches something out. If you've ever played a really intense game of tug of war or just stretched a rubber band super tight between your fingers, you've created tension. In a building or a bridge, the parts that get pulled tight like this to hold the whole thing together, engineers call those ties. Now, these forces are incredibly easy to spot when we think about everyday stuff. We know tension is pulling, but what about compression? Well, that's a pushing force that squashes something down. It's exactly like when you plop down onto a really soft sofa cushion and squish it. Then we have torsion, which is a twisting force. Imagine wringing out a soaking wet towel at the beach to get the water out. That twisting action? That's torsion. And finally, shear. This is a sliding force where parts are pushed in opposite directions. Think about how the 2 blades of a pair of scissors slide past each other to slice through a piece of paper. That sliding is shear. Okay, so let's see how these invisible forces actually dictate the shapes we use to build things. Check this out. If you build a square frame and just push on one corner, it totally wobbles and collapses into a slanted diamond shape. Not great for a building, right? But the triangle. The triangle is the ultimate hero shape. We call this triangulation. A triangle is literally the only shape that cannot be pushed out of shape without breaking the material itself. When you push on it, the forces are perfectly shared by all 3 sides, so it locks perfectly into place. And that, my friends, is exactly why you see triangles everywhere in heavy roofs and those massive tall cranes. All right, now that we know our hero shapes, let's flip to chapter 2 and meet the villains, structural failures. What actually happens when those pushes and pulls are just way too much? Well, when structures can't handle the forces acting on them, they fail. But they don't just randomly break, they fail in very specific ways. First up is fracture. This is a clean break, crack, or snap. It's just like grabbing a wooden pencil and snapping it in half with your bare hands. Next, we have buckling. This happens when there's way too much compression, causing a material to bend or fold in on itself. Think about pushing down really hard on a plastic straw until the middle suddenly just folds over. And then there's toppling, which is exactly what it sounds like, falling completely over, like a really tall tower of wooden blocks getting pushed off balance. Let's pause for a second. We're going to do a little activity to test out those detective skills you're going to need for your exam. So imagine you are the lead engineer on a big project. You're looking at a diagram of a newly built wooden bridge. Right in the exact middle of the bridge, there is a massive, super heavy dump truck sitting there. As an engineer, where should you look first to predict a structural failure? Take a second, evaluate the design. Where is the weakest link? What do you think? Did you guess the joints? Because if you did, you hit the nail on the head. You see, Engineers have to act like detectives by constantly searching for the weakest points in a design. The joints, which are just the spots where two pieces are glued, nailed, or tied together, are almost always the weakest parts of any structure. So if that dump truck's weight is pushing down, you'd want to check exactly where the horizontal beams meet the vertical supporting columns, because that right there is where a fracture or buckling is most likely to start. Great job! Awesome! Let's leave static, unmoving buildings behind for a bit and turn to Chapter 3, Mechanisms. This is where we make things move. Mechanisms are basically motion translators. They take one type of movement and magically turn it into another. Take a look at these gears. Gears are just wheels with teeth that pass movement from one part of a machine to another. See the blue one? That's the driver gear. That's where the movement starts. Kind of like when you push the pedals on your bike. The driver then moves the red driven gear. But notice the golden rule in engineering here. Touching gears always spin in opposite directions. If you actually need them to spin the exact same way, you have to add a third gear right in the middle, that green idler gear, to flip the direction back. Make sense? Now, let's step it up a notch and look at a slightly more complex mechanism called a cam. A cam translates a spinning motion into an up and down motion. Here's exactly how it works, step by step. Number 1, a shaft gets a spinning or rotary motion from a motor. 2, the oval-shaped cam rotates right along with that shaft. 3, a straight rod, which we call a follower, rests right on top of the cam. 4, as the cam spins, the high, pointy end of that oval pushes the follower up. 5, when the flat, low point comes back around, the follower drops down. And 6, just like that, we have successfully turned spinning rotary motion into bouncing up and down or reciprocating motion. It's literally the exact same concept that makes the needle on a sewing machine bounce up and down. Now, both a cam and a crank do essentially the same job, turning spinning motion into back and forth motion. But when we compare them side by side, we see they're used for very different reasons. The big takeaway here is control versus power. A cam uses that funky oval shape for light, controlled tapping, which makes it perfect for delicate moving parts, like inside a little musical box or a wooden toy. A crank, though? A crank uses a really powerful offset arm to violently pull and push a connecting rod. It's incredibly strong, so it's the absolute perfect choice for heavy-duty tasks, like powering a bicycle pedal or moving those heavy metal pistons inside a car engine. Moving right along to Chapter 4. To be a great engineer, we have to learn how to communicate our brilliant designs. So we're going to look at the secret language of builders, engineering drawings. When engineers draw their ideas, every single line on the page has a very specific meaning. Just like periods and commas tell you how to read a sentence in a book, line types tell a builder exactly how to read a drawing. Outlines are dark and thick. They show the visible edges you can actually see from the outside. Hidden detail lines are drawn as little dashes. They show secret edges that are hidden inside or behind the object. Center lines show the exact middle of a circle or a hole. And dimension lines, they always have arrows at the ends to show the exact size or measurement of a part, making sure it gets built to the perfect scale. All right, time for another quick pop quiz to test your visual translation skills. Take a look at this 3D isometric drawing. Can you spot the different elements we just talked about? Notice those dark, solid lines shaping the outside? Yep, those are your outlines. Now look really closely at the dashed lines cutting through the block. Those are the hidden details, showing us that back corner that we can't actually see from this specific angle. And right down at the bottom, see the line with the arrows pointing outward? There's your dimension line, telling the builder exactly how wide this block needs to be. You're getting the hang of this. Chapter 5. This is where we take our flat drawings off the page and fold them into the real 3D world. We're talking about nets and packaging. Have you ever stopped to wonder how a perfectly flat piece of cardboard becomes a juice box? Well, it starts out as a net, a flat 2D shape that folds up into a 3D object. But to make a net that actually works, you have to follow absolute rules. First, all faces must be present. If you're designing a cube, you need exactly 6 square faces. No more, no less. Second, you absolutely must have extra little flaps called tabs, because otherwise you have nowhere to put the glue to hold it together. Third, fold lines have to be marked with dashes, so the builder knows to fold, not cut. The sizes have to be mathematically perfect, and when you fold it all up, absolutely no faces can overlap. But hey, as modern engineering detectives, we also have to evaluate design improvement. We have to ask, can we use less material to reduce waste? Can we design this net so there are 0 offcuts to throw away? Really good packaging isn't just about perfect geometry. It's about being smart and minimizing our environmental footprint. And that brings us to our final chapter, Chapter 6. You've got the shapes, the mechanics, and the packaging drawings all figured out. Now you have to decide what actual physical stuff you are going to use to build your amazing designs. Every single material out there has different properties, and you have to ask yourself what your project actually needs to survive in the real world. Does it need strength to hold massive weight like the steel beams in a skyscraper? Does it need flexibility to bend without snapping, like a rubber band? Does it need toughness to take a sudden hard hit, like a wooden baseball bat? Or maybe it needs corrosion resistance so it doesn't rust, like plastic. But listen up, because here is where you really need to put on your environmental detective hat. Standard plastic lasts pretty much forever in a landfill, right? So a huge design improvement is choosing biodegradable materials or recyclable cardboard instead. Figuring out a material that is strong, functional, and environmentally friendly, that is the ultimate sign of a truly successful engineering design. And there you have it. You now know how to lock a structure with triangulation. You can predict exactly where a bridge might buckle, translate spinning motion into up and down motion with a cam, read a dimension line like a pro, and fold a 2D net into a 3D box. You have successfully completed your engineering detective training, and I'd say you are more than ready to totally ace those exams. So, my fellow detectives, I want to leave you with this final exciting thought. Now that you have the complete toolkit to understand any structure in the world and the knowledge to protect our environment while doing it, what will you build next?